All right, hi everyone. Happy New Year. I think everyone had a great year, but we are gonna continue doing our learning sessions and sharing sessions. So today I'm gonna talking about the Snark versus Stark part 2, especially about this video, Zero Knowledge ZK Whiteboard Sessions Module 4, Snarks versus Starks, and part 2, FRIs. Last time I talked about the air. This time I'm going to talk about the fry from this video. It took me quite a while to actually understand the concept, I think. So fry is what this means. It's a fast, read-solving interactive oracle proof of proximity. That's the full length. Or it's going to be fast RSIOPP. So fast, read-solving interactive oracle proof of proximity. So, yep, that's it. And what does fry do? Let's say, if you remember, we have the polynomial from the air, from the arithmetization section of the Starks. After that, we have the polynomial. Now we're going to create a setup. We need to set up a domain to evaluate, and then we're going to evaluate this polynomial on the domain. And then we're going to do the folding. Folding is technically lowering the degree of the polynomial. So we have the long values of evaluation. So it means it's a long degree polynomial. So we have to fold it. So it means we're going to create the smaller value. We are going to evaluate one more time until it is constant value. And then in each folding, we're going to create Merkle tree hashes for each fold. So let's see the example. I'm going to be sharing my screen. So this is the sample Excel file that I'll be using. So I think it will be easy to understand, hopefully. I'll be adjusting the window a little bit more. And I'm sure this is more visible now. All right. Okay, so let's start. This is just a sample test polynomial. This is a 3-degree polynomial. And we just set a finite field, let's say F17, and domain size is 8, just randomly. I'm trying to choose it, make it smaller, so it will be easier to calculate the whole steps. And domain generator, we are choosing 3 as a domain generator, and we are evaluating this. We are creating a finite field. We are creating the domain values within the finite field 13. This is the domain generator tree, and we are evaluating on the degrees as a multiplicative group on the degrees, and we are just doing mod 17. So this is our domain values we are creating, and then now we have to evaluate the polynomial every domain point. This is the polynomial, this is the domain, and we are evaluating the points. So this is the evaluation of the points, and then I'm just doing again mod 17 because we are using finite field. So it has to be, everything has to be finite field, and this is the evaluation vector. This is the value. And now this is the Merkle root, creating a Merkle root. This is my, again, indexing in domain, and this is the evaluations. This is using Excel, so I tried to replicate the hash function, but this is not actually a hash function. It's just technically taking this number, creating the ASCII value, adding it, and then again doing modulo. So I just want to make it 8 values, and then trying to make it into hexadecimal. So technically it just looks like hash function, just because it just generates hash. This is the Merkle root of this, the first evaluation of this values. Okay, let's come back to folding again. I'm going to talk about it. So this is our polynomial, this is our domain, this is our evaluation vectors. And in order to keep folding, we need to make them pairs. So if we have the evaluation vector, we need to choose a point, 2 vectors, 2 pairs, in a way that one is the mirror of other. So for the simplicity, I'm just choosing one next to each other, 1, 3. So we have the 4 pairs because we have 8, domain size is 8. And this is the formula. This is for the folding formula. What it does is technically separates from the odd to the even. I did not really get it properly, but I think it is what it does. But this formula gives us a value. So what we're going to do is we are going to evaluate each pair, like let's say 1 and 3. We have the 1 and 3, and 1 is going to be x, 1 is going to be minus x. 1 and 3, and at the end, if we evaluate, we have the random value. If we evaluate, we're going to be 18 again. We're going to be using indefinite field. At the end, we have 4 values. And we take these 4 values, we make them again another group, and we evaluate them on the same formula again here. Again, this pair, this becomes 2, and then at the end, it becomes 1 value. So the final value is 2. And in each folding stage, we are going to create Merkle root for each of them. For example, after this is the first before folding. In the first folding, we have this Merkle tree, and then after that, we have this Merkle tree. So this is going to continue until it reaches just 1 value. And then we are just going to send to the verifier. What we're going to send, we are going to just send it to the evaluation points, what points we have evaluated on, because it's going to be long part, and the verifier just chooses a random point index. Let's say we choose random index 0, and we're going to use the first pair. We are going to evaluate on the verifier side again. We are going to create we're going to find this value, and then we try to check this value with the hash, with the Merkle root. So if they did not actually modify the value. So what the prover provides is the value, after the first folding, this is the value for the first pair. We're not checking all, we're just checking 1 0 index. And then we are gonna be provided another sufficient roots from the Merkle tree. First sibling, upper sibling, and Merkle root. So we are gonna take this value, we are gonna compute the hash, and then we are gonna compute the hash of this one and together this one. It's gonna generate another, like the upper sibling, and you're gonna take both upper siblings, and you're gonna create the root, and they are equal. So this is success. It is correct. We just checked 1 folding, and it's going to check another folding until the last one. And it might choose random 5, 6, maybe more values, not just 1. So I just did it for the simplicity, and this is how it works. This is how it checks. So, yep, but that's all. I think this is what I technically understood, and see you guys tomorrow. If you have any ideas, if you have any corrections, please let me know. And thank you.